All right, let's go ahead and get started. I'd like to welcome everyone. I'm Eric Jebsen, the chair of the Chicago section of the American Nuclear Society. I'd like to welcome you to our February joint meeting with the Michigan, Ohio section, which is, it's been a long time that we've had a joint section meeting like this. So welcome everyone. We have a great series of speakers tonight. I think illustrating the very wide, the breadth of work that's happening in the nuclear industry right now, and folks sort of pushing back the edge of the unknown and gaining new knowledge. And in a second, I'm going to turn it over to Dr. Barry Muller, who is the chair of the Michigan, Ohio section, and to introduce our speakers and carry things along. I have a few logistics. One, if you wouldn't mind, those with questions, go to the Q&A feature. You'll see at the bottom of your screen and type your question in there. And then I'll try to monitor those, and Dr. Muller will monitor those. And we'll, I think we'll pause for questions after each speaker. We have 3 tonight. The recording will be posted on the ANS website in a day or so. So if you're interested in hearing it or want to play it back for folks who didn't have the chance to hear it, you have that opportunity. And also, there'll be some final, I guess, verifications, but we plan to post the 3 presentations. So, and that'll also happen in a day or so as we get to them. So with that, I'll turn it over to Dr. Muller and thank Dr. Muller for organizing this. He did the legwork on and making the contacts, and then to our speakers who put together the work that the presentations, and then to Dan Goldberg from ANS National, who is always so helpful in especially the technical logistics of getting these organized. So with that, again, I'll ring off and be monitoring the Q&A, and Dr. Muller, over to you.
All right, thank you, Eric. And again, I welcome everybody to tonight's the February 2024 local section ANS meeting. It's been a long time since we've had this kind of meeting. Just to give you folks a bit of history who are joining us, this is something that the Michigan and later Michigan, Ohio section has done for years, is having, and it was done originally at U of M NARES, is having a student meeting. And with today's tech and what we've learned since over the last few years, we're now doing this virtually and are happy to welcome students from other universities besides U of M to get together and hear what people are doing research-wise in this industry. So the way I'm going to run this is we have our 3 speakers. I will introduce each one, give a short bio, and then turn that over to that speaker. And at the end of their presentation, we'll open it up for a little bit of Q&A there. Probably won't go any longer than 5 minutes if it goes that long. And then I will introduce the next speaker, and we'll do that until the end of the meeting. So unless there's any questions, I can take those right now real quick. If there's a couple short questions, I'll stop for a second. All right.
Barry, we don't have any questions so far.
Great. All right, so our first speaker is from Ohio State University, is Vinicius Zanardo Rodrigues, who got his bachelor's degree in energy engineering in Brazil at the Federal University of Grand Dourados in 2021. Currently, Vinicius is a PhD student in nuclear engineering, focusing on reliability and risk engineering at The Ohio State University. Under the guidance of Dr. Carol Smits, he's developing a probabilistic risk assessment models to analyze the reliability of thermal power dispatch systems for flexible nuclear power plants. Vinicius strongly believes in the potential of nuclear energy to play a vital role in meeting the world's energy needs while reducing carbon emissions. Alongside his research, Vinicius serves as the president of the American Nuclear Society student section at The Ohio State University. Vinicius, turning it over to you.
Hi, everyone. Good evening. So thank you very much, Dr. Muller, for the kind words. I'm pretty happy to stay here tonight to representing ANS at the Ohio State University and to be able to present my work for all the attendees. So let's get started. Please let me know if you can see my screen.
Yes, we can see it.
All right, so thank you. So the work that I want to present today is my current work. My research is about the fault tree analysis for innovative thermal power dispatch system for nuclear power plants. So before we dive into the motivation of our work, we always like to reinforce the importance of probability assessment studies for nuclear applications. So for PRA studies, we need to ask for ourselves and try to answer those questions. What can go wrong in the system? What is the likelihood for failures happen in the system? What is the consequence of the potential of those failures if occur in nuclear systems? So with those three questions, we can build a reliable and consequently a safe project. For example, the current fleet of nuclear power plants to avoid accidents like 3 Mile Island, Chernobyl, and Fukushima. So this is the point that I like to present for people. Why nuclear is so safe right now is because of one of the points is because of probabilistic risk assessment studies that make sure that the technology is safe. So the current goal, the DOE and our university has is to make how to make the current fleet of nuclear power plants more economically competitive with the other source of energy. So going along with the light water reactor sustainability program from the Department of Energy, our goal is to how to make nuclear power plants flexible and in operation generation for our to use the high quality steam that nuclear power plants can provide to not only production of electricity but other products that is high available for the American industry. For example, hydrogen, ammonia, and desalinization, and many other products. So our case of study at the Ohio State University is looking closely to BWR reactors and how to couple with those type of reactors hydrogen facilities for hydrogen production. So getting advantage of the high temperature steam that nuclear power plants can achieve. So the importance of our studies and the motivation of our study is, okay, this is the goal, but how we can make this safe. So we are studying, and I will present here in the next slides, how impactful would be, is one of the questions, how impactful would be to have a hydrogen facility close by to a nuclear power plant. So what is the current, what's the potential risks and hazard that those type of facilities could represent for a nuclear power plant, as well as, and this is the focus of this presentation today, is how it could be the impact of the interface that will connect the nuclear power plant to the hydrogen plant. So this interface that will extract heat from the mainstream line of the nuclear power plant could represent to the reactor itself. So let's go to it. So our proposed system is, we have the BWR reactor design. So the goal is to extract heat, exchange heat, and send this new heat to the hydrogen facility. So the system that we are proposing is a thermal power dispatch two-phase loop that we promote this heat exchanger to warm up water and send high quality steam to hydrogen, to the hydrogen facility. So our system is decomposed in 3 major points. So the TPE, thermal power extraction system, that is connect directly to the nuclear system, a loop that provide this heat exchange, and the HESV side, that is technically is the part that connect the hydrogen facility. So looking into this design, we have major components, for example, heat exchangers, pumps, and valves. Looking specifically to this design, we are planning to be able to extract between 1 to 15% of mass flow. So it will be a flexible interface as well. So we can operate in different levels of power. Operating at 15%, we'll be able to extract 150 megawatts thermal, specifically for hydrogen production. By the time the demand in the grid for electricity will be low, so we can send this part of the power to another use. So going down in the research, we investigated how reliable is our design. So going down in the fault tree analysis, we start to map down what with a main point, for example, a top event. So in our case is no heat was transferred in one of the locations. So we start to try to understand going levels down in the fault tree where failure could happen, to understand how this failure can trigger top event. So we start with a main point, top event, go to subsystems until we arrive to basic events. So map down the system that we have. We see many locations that failures can happen, that potentially could trigger the top event. So for example, heat exchanger subsystems, specific valves, pumps, some of those components. So the methodology that we use to develop the fault tree, like I mentioned quickly before, is systematically broke down the system level by level until we reach basic events. So we did this following the thermal heat flow to become easy to understand how the system works. Looking the most prominent points for failure of components until we reach the basic event. For example, a pump failed to run or failed to start, a valve failed to open, close, failed to control as well as per operation, or in the case in a heat exchanger, tube rupture or leaking, some point like this. And so to perform the calculations that I will explain in the next slide, we use nuclear industrial data. So the data that the nuclear industry already have for those type of components. This data set is generic because in our area it's quite difficult for us to have access to specific data, but it's general, so was good enough so far. But before we dive into the deep calculation, we made some assumptions to get started the analysis. So one of the assumptions was the system is under a single demand, which means that when the system is allowed to be online, all the pumps, all the valves will be under just one demand. So you open or run or start. Are not assuming that you just close again, that it generate one more demand. The mission time of the whole system will be over 3,000 hours. That we assume that will be 25% of a normal refilling period of a BWR reactor, that is 18 months normally. And inside of our system, we have 500 feet of pipes. In the case of a failure of a component, we are now providing repair. So just to see how reliable the system is without repair in the case of failure. So to perform the calculations of reliability calculations, we use Sapphire. Sapphire is a software developed by INL. It's one of the best software for reliability and risk analysis. And so in the case of the basic events with failure mode per time, we use this type of calculation per demand is another type of calculation, just to agree with the data that we have. So the results that we got is represented here. Here is only the top 5 cut sets, because the system is big, so the cut size generated is huge. So I was not able to present here, but we can see what type of components have more impact to the top event. For example, here, a valve TPE1 is more prominent to fail, that could lead to the top event. So here I show you what are the components that have more prominence to fail and trigger the top event. So going to the discussion, we emphasize that we only perform right now to one single demand, one single component failure, which means that the component is failure by itself. We didn't consider at this point common cause failures. In the case of a component was maintained by a crew, another valve close by was maintained as well in the same way, but a mistake was included during the maintenance. But this is a point that we have the future work. But at this point, we only focus on a single component failure. As well as the system intermittence, we make scenarios where the intermittence of the system going online or not is different. In our case right now, we simulated with one demand, but in a real world, with the TPD operating in a nuclear power plant, the levels of demand, so the intermittence of the system would be higher. As well as we measure the single failure coefficient in the case of if one component was not able to perform the safety work or performance, what could go wrong in the system and how this failure could propagate. So in the case of loss of coolant in the TPD building, the contamination of this coolant as well in the case of a leakage, for example. With this analysis as well, was able to allow us to see, okay, where redundancy is necessary, where redundancy of components necessary to increase the reliability and potentially increase the safety of the system as well. For example, strategic pumps, strategic valves, components like this. So the conclusion to our work was that fault trees is a really powerful analysis to understand how risks can originate in a system and how we can address the system in, during the design phase. Another point was where failures can happen, how failures could happen in our system, and how we can introduce redundancy levels to augment the reliability of the system as well. So by identifying critical points where failures cannot happen, if happen, how impactful will be as well. And yes. So the future work, most of those here is already performed. We are already write a paper on this. Is to investigate common cause failures. So how those type of things, when components fail at the same time or in a really short time, could impact the whole system. According to main literature, this is one of the most impactful failures in nuclear applications because of the redundancy layer that we are required to include in the system, as well as what locations, because of the redundancy, CCF events could be more prominent. For example, heat exchanger, pumps, similar valves that is close by. And the current future work that we are performing as well is to expand the PRA analysis. So how our system impact the whole overall system in the nuclear power plant. So we are looking event-trees. If our system fails, how the other system will trigger to diminish the failure. Understand how the system could impact, for example, core damage frequency or early release frequency as well. So we acknowledge DOE for the Nuclear Energy University program for partially fund this project. The first author also acknowledged Ohio State University for the fellowship that I received in my first year. And the authors also acknowledged Dr. Shi from RPI for his contribution in the thermohydraulic development of the TPD system that I just presented. So this is the end of my presentation. So thank you very much, and I'll be open for any questions. Thank you.
All right, thank you very much, Vinicius. Well done, interesting work there. I think I'll turn it over to Eric for his, looks like there's a question down there, and then I do have a follow-up question as well. So Eric?
Oh yeah, thanks. Yeah, Vinicius, very, very interesting. I have a little bit of a PRA background myself, so I was very interested. I've been away from it from a number of years, so it's very interesting to see a fault tree back again and try to remember which ones are the ands and which ones are the ors. So here's the question we have. It's a very good question. So related to the actual production of the hydrogen, do you have any sense of how far from a nuclear plant can the steam travel down a pipe without losing so much heat that it's not very good for hydrogen production? And are there any plans to, say, for safety's sake, pump the hydrogen gas away from the plant in an emergency? So it's a two-part question.
Great question. This is a really nice question that we are looking as well. I'm not personally looking that deep in the question because this is more thermohydraulic point of view question, but we are performing PRA analysis to understand how impactful it would be to have a hydrogen plant close by in the case of explosion detonations. So how those type of events could impact the safety of the reactor. This work is under development right now, so I cannot mention some numbers, but some literatures, for example, from INL, say that if we put a hydrogen plant over 400 meters from the nuclear power plant. In the case of hydrogen detonation or explosion, the safety of the reactor will be now like diminished by orders of magnitude. So will be inside of the NRC regulation. So if you can prove that hydrogen plant could stay closer for us to reduce thermal losses and low losses as well, to pump this steam to the hydrogen plant, will be we can advocate with NRC that this is feasible and you now represent major risk for hazard for the nuclear power plant.
Okay, very good. Thank you. Let's see. And that's the one question so far. Barry, you had a question yourself or follow on?
Well, that was actually the along the lines what I was wondering about. I was looking at, I got the sense, maybe it was incorrect on my part, that your work, of course, is important, looking at what a failure could do to the plant directly. And I was thinking about the possible failure modes of a hydrogen facility that was, then involved in the same kind of event of a run back or issue like that, and how it would respond to that, and what its probability for having an accident. But I think that's a little bit out of scope of the work that you're doing right now. But makes me wonder about that, because at Davis-Besse, where I work, we are actually in the process of putting in a green or blue hydrogen facility on site right now, but I think they're not using steam directly. I think we're using electricity that's taken from the plant. And so, I mean, there's probably different types of failure modes that you'd be thinking about under those circumstances.
Yeah, it's the idea of a hydrogen. We can generate hydrogen with many different sources. Steam is the way that we are looking for right now, but bioelectricity as well is possible. But the main concern that we have in the perspective of PRA analysis and risk assessment is in the case of hydrogen explosion, because hydrogen is really inflammable. So how this can impact the nuclear power plant? So this is the main question that we want to answer. For example, a hydrogen explosion or detonation probably not able to directly damage the reactor containment. But for example, in the case of the Swiss yard, so if you have a loss of site power, and this is an initiate event that can trigger so many points inside of the reactor. And so we deal with Swiss cheese theory that there's looking for holes in that cheese that can pass through, and we can have a core accident, for example.
Yeah, that's interesting. I wish some of our engineers that were involved in the project were on the meeting tonight. I did put out an invite to the plant, but I don't know if anybody signed up, unfortunately. I'd like to thank you very much again for presenting.
Thank you.
If we have some time at the end, and if there's any other follow-up questions, we can entertain them at that time. But fairness to the other presenters, let's move on to our next presenter. Again, thank you very much, Vinicius. And the next person up will be Jeremy Mettler. And so Jeremy is a graduate student at the University of Illinois, Urbana-Champaign, studying plasma processing under Professor David Rodrigues in the Nuclear Plasma and Radiological Engineering Department. His research has focused on plasma etching, plasma diagnostics, and high-power plasma laser interaction. Jeremy particularly enjoys teaching of all forms and has been active in the classroom as a guest lecturer for several courses as the professor of record on an introductory energy sciences course. Jeremy hopes to continue to pursue his love for teaching by pursuing a career in academia. Outside the lab and the classroom, Jeremy is an avid aquarist and rookie gardener. He also enjoys bouldering and skiing in his free time. So Welcome, Jeremy. Looking forward to your presentation. I'm going to turn it over to you now.
Wonderful. Thank you very much for the introduction, Dr. Muller, and thank you all for those who are tuning in this evening. I'm really excited to present my work this evening on measuring fluorine radicals and etching plasmas. So without further ado, I'll jump right in. If I can get the slides to advance. There we go. Okay. So just starting off with, I'm going to hide the meeting panel. There we go. Okay, so starting off with just a quick primer on plasmas to make sure we're all on the same page. Plasmas are the fourth state of matter, and they are a high energy, although not necessarily hot, mixture of free ions and electrons. And oftentimes they also consist of neutral and radical species, which is going to be the focus of this talk. But it's the charged species that make plasmas unique amongst the states of matter, because it allows them to conduct current and to respond to electric and magnetic fields, which some materials in the other states of matter exhibit those properties, but all plasmas exhibit those properties, which makes them unique. They can exist in all shapes and sizes and at a wide range of temperatures, as evidenced by the plasma on the individual's finger in that picture up there, as well as the vast plasmas that fill up large portions of space, like the nebula seen down there. So there we go. So one of the primary applications of plasmas that we found is in semiconductor manufacturing. And so some of the three main basic processes of semiconductor manufacturing here: lithography, which is when you write out the pattern onto a computer chip; etching, when you remove material from the computer chip; and deposition, when you add material to the computer chip. If you take these three steps and you combine them in hundreds of iterations, you can end up with some pretty complex structures like the ones that are allowing us to have this meeting this evening. And in fact, all three of these steps now incorporate a plasma in some way, shape, or form. For this talk, we're going to focus on etching, the removal of material. Traditionally, etching has been done using chemical processes like acids to remove just chemically material from a surface. However, the downsides of that are that it produces these isotropic etches where you get this kind of bowl shape forming. And that's not very well suited to making fine structures like what we need on a computer chip. And so we incorporate plasmas to provide energetic ions, which can help to produce nice, sharp, clean walls like you see down there in the bottom right. And it's the work of both the ions, which provide the anisotropy, but the radicals, which actually do the etching, they produce the volatile product that allows you to remove material from the wafer surface. In the case of like a silicon etch, for example, you might use fluorine radicals to form SiF4, which is then removed. And the key is that you want to get etching to proceed uniformly across the whole computer chip. You want to be able to make sure that the devices near the edge of the silicon wafer work just as well as those near the center. And for that, you need both a uniform distribution of ions and electrons reaching your wafer surface. Ions are relatively easy to measure. They're charged particles. There are lots of different techniques for measuring the population of ions in a plasma. Radicals are highly reactive and very, very short-lived, and they're neutrally charged, and so they are a little bit trickier to measure. Historically, they've been measured primarily using spectroscopic methods. However, the downside to that is that it is not spatially resolved. And so you can get a volume average of the radicals in your process, but you can't resolve how many radicals are at a given spot. And so it's difficult to ensure from a design standpoint that you're getting a uniform flux of radicals across an entire workpiece. And so the goal of this work was to try to investigate to see if we could come up with a way to measure radicals in situ and spatially in a way that's spatially resolved. And so fortunately, there's some work that's been done to this effect in the past with other types of radicals. Not fluorine is used in etching, but things like hydrogen, nitrogen, and oxygen. And that's using radical probes. And so the way a radical probe works is you typically take one or two thermocouples that can measure temperature, and you coat one of them with a catalytic coating, as you can see there with a little gold coating on the right. You expose both of these to a plasma, and if you've picked a catalyst that promotes the recombination of the radical you're interested in, so let's say hydrogen recombining to form H2, that's an exothermic process, and so it releases some energy. And if you have a much higher rate of recombination on one of your two thermocouples, you'll get a larger temperature response. And so you can measure that temperature difference, like you see on the curve down there in the bottom left. You can compare that temperature difference with the rate of recombination that you know for your gold and your stainless steel surface. And you can do some math, and you can back out that the radical density should in fact be proportional to that temperature difference that you've measured. That works great for things like hydrogen, which readily recombines on a wide variety of catalytic surfaces, but primarily gold is what's used for these probes. But this has not been applied to fluorine in the past, partially due to the intensely corrosive environment that's found inside of fluorine plasmas. They like to etch lots and lots of different metals, so it's a pretty punishing environment to put an intrusive probe in. And also the fact that somewhat counterintuitively, while fluorine reacts very readily with metals, it actually has a relatively low recombination rate with itself. And so it has a low tendency to actually undergo this recombination reaction to form F2, and that can make it a little bit tricky to measure. But despite these caveats, we set out to try to apply this concept to fluorine. And so to that end, we built a chamber that we could introduce a couple of different fluorine-containing gases in, both SF6 as well as NF3. And we have a plasma source on the top, a helicon plasma source. And we can run this chamber at a variety of different pressures and flow rates and plasma powers. And we sought to see if we could just at first find any material that might be suitable for acting as a catalyst for this fluorine recombination reaction. And I'll spare you all of the materials that we tested that didn't work and just jump straight to what we first saw had some promise, and that was actually gold, just like with hydrogen. And so here's an example of some of the results we obtained with the gold and a alloy probe next to each other in an SF6 plasma. The first run here, where the number 1 is just a plain argon plasma, so there shouldn't be much recombination or any reaction going on the gold surface. And then 2 through 7 are an increasing power scan. And so we see, as we introduce SF6 to the plasma, we see the temperature difference between the two probes increases as a function of the power. And the power is a good stand-in. As we raise the power, the density of the fluorine should increase as well. And we actually can measure that using the spectroscopy I mentioned earlier. And when we compare the difference between the temperatures of the two probes and the density as measured by actinometry, we get generally the same trend across the power range we've scanned, although you can tell that as we get to higher and higher power, the rate of increase of the temperature difference seems to fall off a little bit there, just as the fluorine density is increasing. So that's a little bit curious, and I'll talk a little bit about why we think we see that later on. But generally, we're seeing a trend that's promising. Some bad news is that, unfortunately, the environment is quite punishing, and after some time, anywhere between 3 and 15 hours, depending on the probe, we were noticing that the probes were failing. They would suddenly, the temperature difference between them would start to collapse and then go to 0. And we suspect that that was due to deposition happening on the probe surface. And so we tried sputtering, applying a bias to remove that material from the surface. And while we were able to restore some activity, it wasn't a foolproof way to recover the probes. So that, coupled with the issues we saw in getting agreement between the radical probe and the spectroscopic measurements, led us to reconsider a few things. And so the first one was, in all the previous examples I've shown you, we evaluate these radical probes at equilibriums, thermal equilibrium. So we let the temperature run out until both the reactive probe and the non-reactive probe have reached a steady state of sorts. And this is fine in probes that have a long lifetime. You could run some long scans and measure each condition, but since the lifetime of the gold seemed to be quite limited, we wanted to try to optimize how many measurements we could take for a given probe. And so we looked at ways to analyze the probes off equilibrium. And so if you consider what the system looks like as you have the plasma on and then suddenly extinguish the plasma, you can come up with a few heating and cooling terms. If you group the heating terms as radical-driven and non-radical-driven heating terms on the catalytic probe, and you assume that those extinguish rather quickly as the plasma is extinguished, which they do because all the species are very short-lived, you can come up with this relationship where you relate the slopes of the curves now, instead of just the temperature difference, the difference between the slopes of both a catalytic curve and a non-catalytic curve to this overall heating term due to radicals, which then in turn should be proportional to the density of the radicals in the vicinity of the probe. So that helps to address the shortened lifespan. Addressing the issue of the probes disagreeing with our spectroscopic results, another thing we noticed is that when we applied NF3, which is actually a stronger carrier of fluorine, it actually more readily breaks up into fluorine, we actually saw almost no probe response on the gold. And so that indicated to us that the gold was likely responding instead of to purely fluorine radicals, but was in fact responding to SFX species, so SF5, SF4, which is not entirely useless, but it's not exactly what we set out to measure in the first place. And so rather than use gold, we decided to switch gears a little bit. We're in a very strong etching environment, so why not try to measure, instead of a recombination reaction, which fluorine is particularly bad at, let's try measuring an etching reaction instead, which is also an exothermic process. And so here we did some initial investigations with tungsten, which is readily etched by fluorine. And in run 1, which is argon, we see the probes read relatively close to each other, a few degrees separation. In run 2, we see a very strong temperature response from the tungsten compared to following runs. And we see that temperature response actually decay because we had a very thin coating of tungsten on our probes, and we managed to etch it completely clean in the matter of a few minutes. So we just sort of taking a step back to take an example of what the non-equilibrium measurement would look like. We take the slopes here, that is well suited to an etching probe. And then we take, instead of just a thin coating of tungsten, we apply to a large pellet of tungsten. So here you can see a probe pictured at center where we have an inert probe, in this case, an aluminum pellet on one of the thermocouples, and a reactive probe, the tungsten probe, on the other tungsten pellet on the other probe. And when we stick these into an SF6 plasma, we actually get an incredibly large temperature response. This is much more like what we were seeing in the hydrogen case. So this is another advantage of using the larger pellet style design. And so here we're actually getting pretty consistent etch results. And when we compare them in both SF6 and NF3 to the densities as measured by spectroscopy, we can see that the probe seems to capture well the increased density that we would expect to see in an NF3 plasma as compared to an SF6 plasma. So this was really encouraging that we're actually able to measure not just some side radical of SF6, SF5, SF4, et cetera, but actually the fluorine itself, because we're getting response in not only an SF6 plasma, but in an NF3 plasma, like what we would expect with, according to the density measured by spectroscopy. And this was done using the non-equilibrium analysis. So that was a pretty recent result coming right before the holidays. So we've continued working with these probes in a variety of other plasmas that should be published here shortly. But just to wrap things up, fluorine radicals are a key ingredient in the modern etch process, but attempts to measure them using traditional radical probe designs proved that those, at least the materials we tested, the traditional design was unsuited to the technique. However, by combining a non-equilibrium analysis technique with an etching-based probe, we were able to get some pretty good results for radical densities that agreed with the accepted spectroscopic measurements. So thank you all for your time, and I'm happy to take any questions that anyone might have now.
All right, Jeremy, thank you very much for that presentation. As I understand it, this is work you're going to be continuing in the future, correct?
Yes.
And your next degree, I believe you said at one
Yes.
point. Do we have any questions from the attendees for Jeremy?
This is Eric Jepson. I have a question, and this might be just more of an extrapolation or a sort of a thinking down the road here is, you know, first of all, the whole thing about the bowl versus the sharp edge, I now think I know why my computer with, say, Windows doesn't operate well at certain times, because I think I've got the bowl type chips and not the sharp edge chips. But no, just thinking ahead to like manufacturing, once you determine this, you know, if you can measure the fluorine very accurately, like the application, and this is far down the road, is this you wouldn't need as much fluorine gas. You could, because you know, like you say, it's corrosive. It's nothing you want in the environment necessarily. So, you know, is this like an efficiency type thing in addition to the edging that you talked about? You know.
Yeah, that's exactly right, actually. So they're using fluorine regardless right now in reactor designs. It's just the main application of this is helping optimize the reactor tools that we make for industry, so that we can make sure that the fluorine is uniform across the surface without using too much fluorine, and come up with conditions where we actually have the optimum amount of etching going on. Right now, since they can only measure it just as a volume average, they kind of wade through the dark, pick a condition, see if that produces a good result on the computer chip, which they measure after the fact. And if it does, great, they go for it. But this would actually allow you to put a little bit more educated guess into your reactor design. It could help optimize for more efficient use of fluorine and a more efficient design of the reactor. It doesn't have to be as big anymore to compensate for their difficulty in measuring the fluorine.
Very good. Thank you. Barry, it's up to you. We have one question in the chat. Do you want to take that or go to the next speaker and catch up with this question later if we can?
Let's see, where are we right now? Let's go to the next talk and maybe catch up at the very end with that, please.
Okay, very good. Thank you.
Yeah.
Thank you, everyone.
Yes, thank you again, Jeremy. Interesting talk. So I'm going to move on to our last speaker of the evening is Mackenzie Warwick, excuse me, is a fourth-year PhD candidate in the Nuclear Engineering Radiological Sciences Department at the University of Michigan, with a focus on ion irradiation creep and material performance in coupled extreme environments. Mackenzie is an intern at Idaho National Laboratory researching crystal plasticity and modeling of creep mechanisms for long-term performance prediction. She has previously researched the technical and economic feasibility of isotopic tailoring of nickel in Inconel 718 for low activation purposes as a fusion first wall candidate material. Mackenzie has a strong interest in Japan's nuclear energy sector as she became interested in nuclear energy after the 2011 Fukushima Daiichi accident. She has 12 years of intermediate experience with Japanese and has visited Japan 3 times. When Mackenzie is not in the lab, she is typically running K-12 outreach workshops that she has developed to increase the accessibility of nuclear engineering topics for young students, which is an admirable activity there. Without any further ado, I'm going to turn it over to you, Mackenzie.
Great, thank you for the introduction. Can you hear me on Zoom?
Yes.
Okay, perfect. Perfect. So I've got 5 other students in the white auditorium with me. So there's another set of the audience. But I'll get started on my talk. So this is my PhD research, and this particular talk is discussing our development of tapered specimens for ion irradiation creep testing of 316 stainless steel. And I gave this presentation in December at the Materials and Nuclear Energy Systems ANS conference. There we go. Okay. So I'm going to start with a broad motivation. So there's a ton of new advanced reactor concepts that are coming out with proposed coupled extreme environments, meaning they're significantly higher temperatures, they're at higher doses, so higher displacement of atoms. They'll have different cooling material and moderating material, so you'll have the corrosion aspect and significantly higher stress. And so these are a handful of the new proposed reactor concepts. And if you didn't know, through the NRC licensing process, you basically have to verify that your material that you're proposing to use is going to work in that environment. And so a lot of these concepts propose materials that aren't fully vetted and or do not exist quite yet. And so in order to move forward in the licensing process, you have to verify those. And a lot of these companies do not want to put in the financial resources to do the code qualification of that material. And so, and they do these, they'll do these like proof of concept designs, and they'll build them out of materials that are already qualified. There's like 6 or 7 that are code qualified for nuclear reactors, and one of them is 316 stainless steel, which is the motivation for my material. However, one of the primary mechanisms of failure is creep, and it is actually pretty detrimental, and in the regulations, that's like your life-limiting factor. So if you don't know what creep is, it's a oh goodness, it's why am I blanking? Creep is a permanent deformation mechanism in which you have a combination of high temperature, high stress, and radiation can accelerate the rate at which your material will permanently deform. And so you can see in red, there's the strain equation, which is a superposition of all of these different functions. So you have strain components from your temperature and your irradiation. And so if you take irradiation out of the equation, your material is going to be strained just from the high temperature, which you can see the first component is your thermal creep strain contribution. And when you introduce radiation, it just makes things worse. And so there's 2 primary ways that creep is kind of being defined as, and that's climb and glide. And so you have your initial crystal, which is your array of atoms. And so you introduce a strain by introducing extra rows or planes of atoms or taking them out. So glide is when that plane of atoms moves like left or right in your material until it reaches an obstacle, which you can see is that kind of like gray circle, which you can consider a precipitate. And so once it reaches that obstacle, it wants to move to a lower stress state. So sometimes it will climb to another plane of atoms and then continue gliding, so continue moving. In a lot of cases, radiation creep and irradiation swelling are interrelated because radiation introduces point defects, so like interstitials and vacancies. And so swelling is this accumulation of vacancies. And so a lot of the time it's hard to deconvolute the contributions from each. This is a deformation map of 316 stainless steel. And you can see based on your normalized temperature, so that's your operating temperature divided by your melting temperature, it's normalized. And then you have your stress, so your applied stress on the y-axis. So it's a function of temperature and applied stress. And so in each of these regions, there's different dominating mechanisms. However, in irradiation creep, this regime has about 6 or 7 proposed mechanisms. So we don't fully understand what actually happens. And so that's my focus here. So I did during my literature survey, I found all of the prior work done on the 300 series of stainless steels. So you have 321, 304, and 316 stainless steel. And then I superimposed them onto that deformation map that I basically redone in Python. And so the filled markers are protons, so hydrogen ions or heavy ions. And then the empty markers are neutrons. So it's kind of a good smattering of those. However, I was really interested in the physical reaction, so the microstructural reaction. What does it actually look like? And when you try to find what happens and what that looks like, you have significantly less microstructural data. So they say, oh, this is your strain, this is the dose that it went to, this was the temperature, but nobody actually really knows what that looks like on a microscopic level. And so that's what I decided to focus on. And so obviously before I run any of my experiments, I have to do a characterization of my as received material. So 316 stainless steel is a primarily iron nickel chrome alloy. I purchased 25 micron thin foils, and then I made sure of the thickness, the sample thickness, the grain size, the orientation, etc. And so in the kind of like rainbow picture with the red arrow going across it, that's an EBSD map. It's electron backscatter diffraction. It basically tells you which orientation your cube is of all of the grains, which will be important later. And then on the bottom left, you'll see the sample surface and the thickness, and it verifies that it is 25 microns thick. And then you'll see in the large image in the center, that is a TEM micrograph. And so basically it's the electron micrograph. And you'll see annealing twins, which are basically they're formed based on the heat treatment and annealing process. So this is my current experimental setup. So I conduct all of my experiments in the Michigan Ion Beam Laboratory. And so on the left, you'll see a view normal to your sample, and then on the right, you'll see a view from above. And so I attach my sample to a load train through friction grips. So I place my thin foil between two friction clamps, load it in vertically, and then I attach a load train in which we have a constant load applied to our sample. It is backed up against a copper block. There is no medium between the sample and the copper block to conduct heat, which will come into play later on in the presentation. I use 3 MeV protons to irradiate. And so for like the nomenclature imagery, I'll use like the X symbol in this kind of like how they did the magnetic field, signifying like into the page. That's like the direction which will come in handy. So I irradiate it normal to my sample surface, and then I do a preheat of my sample for 16 to 18 hours beforehand so that my thermocouples can come to temperature and the rest of the chamber can come to temperature, because we can't actually weld anything to the sample or else we're introducing defects. So temperature measurement is kind of difficult. But we do a preheat, and then we'll calibrate our IR camera, in which we then use to track the temperature throughout the rest of the experiment. And then for the strain tracking, we have the capability to do in situ strain tracking. So I roughen my sample surface with 4,000 grit sandpaper so that it creates like a variable topography. We shine a 532 nanometer green laser at that surface. So when it's reflected back into the camera, it creates like this black and white contrast in which we can then have specific areas of interest circled on our sample, and then we can track the strain that way. And so we can track localized strain basically throughout the entirety of my experiments. And the reason I use 3 MeV protons and also super thin samples is that we want a uniform damage profile through the thickness of my sample. And so in order to achieve that, you can do that when you have 25 microns, at least less than 35 microns thick. So it's incredibly challenging to work with, because that's like a quarter of the thickness of a human hair. So here's really the meat of the project. So these are the tapered specimen geometries that we've designed, and that's to accelerate basically the testing of these materials. And so the first iteration was the straight-sided, which means we can only do 1 temperature and 1 stress, and that took 7 days. And so it is an expensive, time-consuming method. And so we tried to pivot into how much more data can we get from 1 sample. And then our second iteration was the taper specimen, in which we could achieve 2 millimeter and 4 millimeter in a gradient, basically. And we could achieve a stress of 316 megapascals in the 2 millimeter and 158 megapascals in the 4 millimeter. And then we've gone on to the funnel, in which it's a little bit more elongated. And then finally, we are on our fourth geometry of the ziggurat, in which the taper is basically uniform on either side. And the reason we did that is because in the first two experiments, we had a significantly smaller radiation area. And we realized with the taper specimen, the heat flux and the heat flow throughout that was quite uneven. And so on the first tapered experiment, we ended up having a temperature spread of like 150 degrees C, and that's kind of hard to do because you're really only supposed to be changing one variable. And so we're hoping that with the ziggurat's geometry, it will be able to have an even heat flux basically through the center and then up and out both of those directions. So I have two experiments that I'm going to talk about. So the purple dashed line is our beam area. The first experiment was our first taper one with an average temperature of 511 with a significant variation of 77 degrees C. And so that's our IR camera in the middle, and then the strain tracking on the far right. The bottom right shows a much better picture of the speckle pattern that is created from our laser speckle excitometer. And so what I did is then I plotted my contributions to the deformation map, and you'll see that they popped up on the right. So that experiment was at a dose rate of 7E minus 7 dPa per second, which is quite low, but it is very similar to what actually happens in a nuclear reactor. So really the only difference is the particle interaction, whether it's charged or neutral. And so you can see that I have a significant temperature spread on the first sample. And then the second sample was significantly better. We increased our radiation area to a 9/7, but that reduced our dose rate and therefore our total dose in 1 week. But you can see that the temperature spread, while 30 degrees C, the average temperature in each of the primary regions we were looking at was very, very close to 550 C. And the microscopy aspect, I'll just be focusing on this experiment. It was irradiated to 0.2 dPa. Okay. Oh goodness. So basically, it's really important for the microscopy aspect. We know that there's loops and dislocations that form on habit planes or close packed planes in FCC structural material. So what we do is we irradiate. We then see our electron backscatter diffraction. Pick a grain that is oriented in the direction we want it to. We targeted 110 just as an initial part. So I did lift outs perpendicular, parallel, and some sort of degree in relation to the stress. So the stress in this case is like the y-axis. And I'm only going to talk about the lift out that was oriented 35 degrees to the axis. So on the right-hand side, we expect to observe multiple different types of loops. So perfect loops, which are atoms that are arranged in, they basically conglomerate, or like they come together and they like literally form loops. And those are not going to have any contrast in the middle of them. But then we have faulted loops, which are like stacking faults. So you've got these loops that come together, and then it's like a bunch of interstitials within that loop. So it's usually dark or light, whatever way you look at it in the TEM. And so for preliminary findings, the whole purpose of this was to see if we can generate multiple data sets from one experiment. And you can see we have very few dislocation loops that are traveling on the 110 plane. That's the primary subplane in FCC material. And they're going towards a grain boundary, which is a sink. So dislocations and defects will go towards sinks. And then on the same sample, in a totally different area, in the higher stress area, you have this ridiculous, you have this significantly more increased like dislocation network. You have a bunch of various different types of loops that are showing up. And so there's different orientations for all of these, and I won't go into it because we're short on time. But basically, this proves that our sample can generate multiple data sets. Whether that is inherent necessarily to the specimen geometry, we'll figure out, but this is the same grain as before, and like I said, and so I found something pretty interesting. I found like these dislocations going towards the grain boundary, and what I did is a microchemical mapping. So I did basically wanted to see the chemical composition of what they were, because in literature it shows that there is nickel silicide precipitates forming, and so what you see is that there's nickel along the grain boundary and then covering all of those dislocations, which proves previous findings. And so we think that there is some type of microchemical aspect that contributes to the acceleration or deceleration of the creep rate overall. And so that will be more further pursued. So in conclusion, basically, with these geometries, we can generate like 3 times the amount of data in one experiment, which then therefore accelerates finding all of these mechanisms out. And then these microstructural results are being used to build a robust database for crystal plasticity models. So crystal plasticity is stress-strain relationship in your crystal. And so if we know what happens on a microstructural level, like density, size, orientation, it can help build these models and therefore predict at what point does this material fail. And with that, references, acknowledgements, that's are the QR code for my LinkedIn if anyone's interested. But I wanted to thank my funding for the Department of Energy. I'm on an NEUP fellowship, and then also with Idaho National Lab. So thank you for listening. I know that was probably a lot.
Well, Mackenzie, thank you very much. That was like you said, a lot to take in there. There's a lot of work on your part. I have a quick question. When you said microchemical analysis toward the end, how do you do that on such a small specimen?
Yeah, so you put it into the TEM, so that's like transmission electron microscope. So we basically take these things called lift outs. You use focused ion beams to kind of mill it out of your bulk material. So the specimen that I've irradiated, then you thin it down. That the lift out images that I showed were about 130 nanometers. And so basically you make it electron transparent, and then you do electron dispersive spectroscopy. I believe that's what it stands for. It's EDS. And basically it measures the energy loss, and based on what like chemical, like the periodic element, basically it's going to have different losses because of the interaction with that nucleus. And so it'll basically map out all of that, and then you can select what what other elements you'd want to see. Like, so I could have done one with silicon to see where the silicon was, but that's kind of how we do it. They take about like an hour and a half to have good statistics.
That's interesting. It's amazing that you could do that in such small.
It's so cool.
That's part of your tool set there, but for me, that's a revelation. So thank you for the explanation.
Yeah, of course.
Eric, do you have any other questions for Mackenzie?
Yeah, I have another one, and this one it came up kind of at the beginning of the talk, and the question is, there was some reference to sandpaper, which I may not have. I thought I heard that too. And such small samples. Could you address? Did you say you sanded it somehow to? I mean, using sandpaper on something as a quarter of the thickness of a human hair, and to get the light, the laser light to give you some sense of depth. Could you talk about that? Did we miss that?
No, you heard me correctly. It is sandpaper. That was like the original. That was like the original way to do it. So yeah, we take like a super fine grit sandpaper, and it is very hard to actually do that without like ripping your sample, bending it, because in that point you're introducing stress and all of these other things that you shouldn't. But yeah, I've used sandpaper. It took a while. We're actually moving to DIC, or digital image correlation. So I'm actually running an experiment on Monday where I use sandpaper on half of the sample and then use high temperature carbon paint on the other side. So that way we're not actually deforming the surface, because based on your grit, you then have a damage depth within your sample. And so previously it didn't really matter because the damage depth ended up being larger than our sample thickness. So it was like uniform damage introduced, but that's not a great way to run experiments. And so we're trying to do it where we're not damaging the sample. Does that clarify the question?
Yeah, it certainly does. And actually, you know, because at one point this is so sophisticated, you're doing, you know, you're down in a nano range, and at the same time you're using something you might find in, you know, your wood shop. So it's just, you know, completely, you know, left brain, right brain, yin yang. It just, you know, I couldn't believe it. So no, that's all for us. So Barry, back to you.
Thank you.
Yes, thank you, Mackenzie. So I want to, I just thought this is one thing we can't do is, I don't know of an efficient way to applaud our speakers for presenting tonight on all their hard work and their effort and their intelligence. It's inspiring. And I do thank you very much. And I don't know, we did postpone one question, Eric, if you want to introduce that right now before we close this evening, if that's still outstanding from, I believe, from Jeremy's talk. Is that, did we table something there?
Well, in the interest of time, can everybody else see the chat? It was answered, both questions. We've got 2 extra questions, and they both seem to be answered in the chat, if folks can look at the chat.
Okay. All right, well, we can deal that. So I guess we're going to close here again. Very much thank you very much. We will do this again next year. I think that it was successful. And if anybody, either the participants or any of the attendees, have any feedback on this format and this type of a meeting, I would definitely send that on to Eric or myself, and we'll go through that. And without any further ado, I think we're going to close at this point. And thank you very much, and have a great evening.
Yep,
Thank you for organizing.
so much. Yep.
Thank you.
Thank you very much.
Good evening.